So like I said, today we're doing the last thing, cross product. We're going to go back over the 3 different kinds of products. We're learning the third one, but again, you notice that I've been kind of repeating this over and over and over again, that we don't just multiply vectors. We have to define what type of product we're doing. Which one are we doing? Partially because there's 2. So are you doing the dot product, the cross product? If you're doing scalar multiplication, that one kind of stands out because you'd have a scalar, not 2 vectors. But also, just generally multiplying is not something that's defined, right? So that's going to be important. We're doing cross product over 2 days. Today we're doing one of the forms, the Cartesian form, and then next day we'll do the other form, kind of like dot product. The other form is not quite as useful as the Cartesian form. The Cartesian form is one we want to use because we're going to be doing all kinds of stuff with on the Cartesian plane in 2 dimensions and 3 dimensions moving forward. But we're going to talk about what the cross product is. The dot product is, the formula is pretty simple, right? I'm sure you've got it memorized already. Cross product's a little trickier, but there is a trick that's going to allow you to memorize it, but you need to know it. Okay, so this one does require more practice, and we're going to learn what it is, and we're going to learn what it does. That's a huge part of cross product. For dot product, it does the thing where it just maps one of the vectors onto the other and then multiplies their magnitudes, right? And that's a little bit of a odd thing. And we're not going to use that concept in this course very much. We're mostly concerned with the dot product, that if the dot product is 0, that means we have perpendicular vectors. But the cross product does something else very specific that we are going to use over and over and over again, okay? Scalar multiplication results in a vector. Again, notice how I'm repeating this. So this is important. It's kind of like back when you started integers and you had to just learn that a positive times a negative results in a negative. And until you just learn that fact, it's not the kind of thing that you're going to figure out necessarily, right? It's not necessarily intuitive. Same thing here. You need to just get used to the fact of what is the result of doing any kind of operation. Does it result in a vector, a scalar, or is it undefined? Dot product results in a Maddie? Scalar, which means just a number, can be positive or negative. Cross product results in a vector. The output of the cross product is a vector. The dot product is between 2 vectors. So the input is 2 vectors, and the output is a scalar. Same with cross product. The input is 2 vectors, but the output is another vector, and that vector has relevance. It means something relative to the first 2 vectors. Okay, so also we want to think about what the input is, and the input for cross product and dot product is 2 vectors. So I could imagine doing something like this. I don't know why I wrote it way over there. The brackets are like bedmass brackets, so it's telling us to do that first. So what happens when I take the dot product of vector A and vector B? I get a scalar. So this is the symbol for cross product. I guess I should mention that. It looks like the times symbol, but in context of vectors, it means cross product. Can I take a scalar and cross it with a vector? No. So this is undefined. One of those little puzzle questions that will be on the test. There'll be several of them where you have to kind of work your way through and decide if each operation in order is possible or not. And then, again, like we said before, you're going to say whether the output is a scalar, a vector, or if it's undefined or not possible. Scalar multiplication just looks like this. It does just kind of use regular multiplication like just brackets, whereas dot product, I'm going to write out both versions. Dot product has to be defined with a dot, and cross product is defined with a cross, like that. Okay, this next little blurb, here you go. You've got it in your notes because I think it's on that handout that I gave you. Hopefully it is. The cross product, this is what's important. This is the result of a cross product, and this is something you absolutely 100% have to know for the next unit. You have to know it for this unit too, because there's going to be some questions that just directly sort of ask you to do this. But in the next unit, there's a lot of kind of problem solving or different things that we're going to be doing, coming up with equations of things and solving systems. And in order to solve those systems, you need to recognize the properties of the things that we're working with. This is going to be a little bit sort of unspecific right now until we actually get into it, but go with me on it. You got to recognize the properties of these things and then think about how you can, like, what you can do to manipulate those properties to come up with equations, to solve systems, that kind of thing, okay? So you need to know what the output is and the relevance of it. The cross product takes two vectors and creates a third vector that is orthogonal to both. What does that mean?
Like parallel, or like you can multiply them to like get to the same value.
Yes, but specifically, not parallel, but perpendicular, right? So it takes two, you're not going to be able to see this in the video, but here's my two input vectors. They can be anything. They're not orthogonal to each other. So let's say I just do this. It's going to give me that. That, or a scalar multiple of it, or the opposite direction, or a scalar multiple of it, are the only vectors that are orthogonal to both. Okay? I can get a vector that's orthogonal to this one. You see that okay? Right? It's perpendicular to this vector, but it's not perpendicular to the other one, is it? Or I can do perpendicular to this vector, but it's not perpendicular to the other one, is it? But if I do this, it ends up being perpendicular to both. So that's what the cross product does. And then it also has a magnitude that's related to something that we're going to talk about in the next lesson, and it's not super relevant for us, but the magnitude sort of has some relevance, but you know, it's mainly the direction vector that we are going to be interested in, okay? That turns out this is a huge part of what we're going to do in the next unit, is we will have two vectors, and we will want to find a vector that's orthogonal to both. So we use the cross product, okay? This is the cross product. That's the formula. I want you to think about the difference between it and the dot product, because this might help you kind of remember it. I'm going to show you a trick as well, but if we compare this to the dot product, it would be A1 times, I'm going to get rid of the brackets, A1, B1 plus A2, B2 plus A3, B3. Cross product really only exists in 3 dimensions. So that's why we had to pause and do 3D vectors yesterday, because cross product doesn't really exist in 2 dimensions. There may be some other similar form, but I mean, you can't have a vector that's orthogonal to 2 vectors in 2 space. Like, that doesn't make any sense. So it's really in 3 space that we do this. So what's happening here? Well, this is how I kind of think about these two things. In dot product, like things are helping like things, and everything's helping everything else. So I'm multiplying the first elements together, the x coordinates. I'm multiplying the y coordinates together. I'm multiplying the z coordinates together, and I'm adding everything up. Notice that this one I'm not adding everything in the end because it's coordinates. There's a comma in the middle because this is creating a vector. Notice the output is a vector. But look at the difference. The x coordinate of the output of the cross product doesn't have anything to do with the x values of the original two vectors. It has everything to do with the y and the z. So it's the y value times the z value, and then the y value of the second vector times the z value of the first vector, and you're subtracting. It's almost the exact opposite of dot product in a way, right? Where in dot product we're multiplying like things together. In cross product we're doing the exact opposite. We're multiplying everything that's not like each other. Okay, so in the first coordinate, I'm using everything except for A1 and B1. In the second coordinate, I'm using everything except for A2 and B2. Notice, it's just 3 and 1 and 3 and 1. And then the third coordinate, I'm not using A3 or B3, I'm just using A1, B2, B1, A2. And always subtracting. Okay, so you can see right away, the formula for this is a little bit more complex. It's a little bit more to remember. Any questions about that? Okay, let's try one. Whoop. So here's the trick. You got to put your pencil down and watch because this is important. The trick is, feels familiar to me like complex trinomial factoring, but we're not doing the same thing, but we're writing out numbers off to the side and using it as a little guide in order to do the multiplication properly. I've seen different teachers do this a little bit differently. This is how I do it. I start with the y values. So I start with 1 and 3. I got to make sure I leave enough space here because it's going to be long writing this out the first time. Then we move to the z values, so 3 and 6, and order matters. We're going to look at this in a minute. So the first vector, which in this case is a, because I'm doing a cross b, has to be on top, and the second vector, which is b, has to be on the bottom. Then I switch over to the x coordinates, so 7 and 4. Then I repeat the y coordinates. So you see what I mean? Like it kind of looks like it's nothing to do with factoring, right? But it kind of looks like that. And it's just a little, almost like an organizer, a graphical organizer. So this is y, z, x, and then repeat the y again. We start with A2 times B3. So isn't this A2 and this is B3 because I started with y and then I did z? So it's 1 times 6 minus A3 times B2. So A3 is 3, B2 is also 3. Comma, A3 times B1, well, isn't that these two? This is the z coordinate from A, and this is the x coordinate from B, so that's that. Are you seeing how this works? And then that. And then finally, 7 times 3, 4 times 1. So we're writing this out nice and long in the first time, but you're going to be doing a lot of that in your head. If you can do 6 minus 9 and go straight to the negative 3, then do that. Or if you want to write down as your first step, 1 times 6 is 6, 3 times 3 is 9, 3 times 4 is 12, 6 times 7 is 42, 7 times 3 is 21, 4 times 1 is 4, negative 3, negative 30, and 17. Now we're going to do B cross A, and then we're going to stop and chat about a couple things. So now I write the B first. So 3 times 3 is 9. 6 times 1 is 6, so 9 minus 6. Some of you that are paying attention and observant are noticing kind of what's happening here, like there's sort of a pattern between A cross B and B cross A. 6 times 7 is 42. 4 times 3 is 12, so 42 minus 12. 4 minus 21. 3, 30, negative 17. So what do you notice? Maddie?
You just flip the sign.
Yeah, they're the same numbers, but opposite signs. And if you think about it, that's going to happen every time. But the other thing that I want to point out, that means A cross B is not equal to B cross A, which this is the first time that this has happened. They're not commutative. This is the first time this has happened. All the other things that we've looked at so far were commutative, meaning order doesn't matter. But for cross product, it does. So you can't interchange them. So that's why if it's A cross B, A's got to be on top and B's got to be on the bottom. Otherwise, you're getting B cross A. Okay? But it is true that A cross B equals the negative of B cross A. That is true. And again, if you just look back at the two, you'll see that that matters. You'll see why order matters. The other thing is when you write these out, you got to start with the right one. You can't do this minus this. That's backwards, right? So we got to do, what's going on here? Whoop. We got to do, start at the top and go down. And then the other one doesn't matter, but start at the top and go down. Start at the top and go down, right? Whether it's 6 times 7 or 7 times 6, that part doesn't matter. Multiplication is commutative. They're both 42. But is it 42 minus 12 or 12 minus 42? That's the part that matters. Okay? And, again, the visual is, if you do A cross B, you get this vector. If you do B cross A, you get that vector, right? So you get the one coming out the other direction. Which direction it's pointing is not going to be relevant for the stuff that we do, but it absolutely is relevant in physics. This is going to be a bad example. If somebody who actually knows things about physics ever hears this, they're going to say, no, that's not true. But I'm kind of making this up. But it would be like if you have two vectors that are making some kind of electrical field, which doesn't make any sense necessarily, but you get the drift. You know what I mean? Is the electrical field coming out this way or going this way, or is the magnetic force like pushing or pulling or something, right? Like it would be something like that. Interaction between two forces, which direction is the output force happening? Okay, that's kind of one way that you could sort of think about it, I guess. But for us in the end, it's not really going to matter. Okay, so try this one. So write them out. Start with A. Start with Y. Y, Z, X, Y. 1, negative 3, 4, 1. Start in the middle. Go around, around, and around. 0, 6, negative 2, 0. I got 6, I got this. 6, negative 18, 2. Is that what you got? What does this one mean? Prove that A cross B is orthogonal to both A and B. I mean, I told you that this is true. You believe me? What if it's all a hoax? An elaborate hoax. How are we going to prove that?
Well, if you use like the close formula, you don't have to use the close formula, but like as long as it's equal to 0, that means it's perpendicular.
What's it called? Come on. Dot product. Right. Yep. Use the dot product to show that they're orthogonal, to show that they're perpendicular. The cross product finds a vector that is orthogonal to both. So I'm going to do A cross B, which we already calculated, dotted with A to show that it's orthogonal to A. So this is 6 times 4 plus negative 18 times 1 plus 2 times negative 3 so it worked for that one. Okay, try the next one. Yep, that one worked too. Very common kind of question that you would find on a test. Find A cross B, show that it's orthogonal to both A and B, or maybe just show that it's orthogonal to B, right? Sometimes, I don't think we're going to do it in this lesson, but in the next unit, we don't care about the magnitude of the output vector. I just need a vector that's orthogonal to the two given vectors. So I could take this and turn it into 3, negative 9, 1, because that's scalar multiple. I've scaled it down by 1/2. Does that make sense? So it's in the same direction as the origin of that one. So it's still orthogonal to both original vectors, right? It's in the same direction, it has to be. But the numbers are smaller, so it's going to be a bit easier to work with, because we don't need the magnitude of that output vector for the stuff that we're doing, generally speaking. Okay? But if it just says find A cross B, then it means find A cross B, which is that. All right. Properties of the cross product. It is distributive. And interestingly, it's distributive on both sides, and because the order of the cross product matters, I can't just take the C and move it to the front the way we would, like you would never see this, 5 plus 4, 2. We'd always write the 2 on the front, but you can't change the order of cross product because the order matters. So this would be A cross C plus B cross C. Okay, a couple more questions and we're almost done. given the following three vectors, find u cross w minus u cross v. Do you want to do it the easy way or the hard way? Easy way, good choice. This is not a kind of question that's going to come up organically or naturally in what we do. This is just a math class question. If one like this is on the test, the easiest way to do it is to recognize that u has been distributed across those two. So I can do u cross w minus v. Why did I do this? Because it's just going to make it easier. Do you want to do the cross product twice? Or do you want to just subtract two of the vectors? That's easier, right? So I'm going to do it that way. If you did it the other way on a test and you got the right answer, it'd be fine. And once you get good at the cross products, it's not that hard. You can do it in one step. Okay? So this is u, which is 1, 2, negative 3, crossed with w minus v, so negative 1 plus 2, 2 plus 4, and negative 4 minus 6, right? Just subtracting. Do you have to show that step? No, of course not. Okay, now I'm going to write these out off to the side. 2, negative 3, 1, 2, 6, negative 10, 1, 6. You can go ahead and finish that one. I got negative 274. We good? Okay, and then once again, these kinds of questions are going to come up all over the place. Find a unit vector that is orthogonal to A and B. How do we do this one? This is where you got to make your plan. How do we do it? There's a few parts to it. Come on.
We could do A cross B and then take the magnitude of that, and then
Right. A cross B, then normalize that vector, which is finding its magnitude and writing each part over the magnitude. Very good. Right? So there's a few steps, and you got to kind of know how to go through the steps. You got to know that when it says a vector orthogonal to both, it means cross product, and then you have to know, well, how do you normalize a vector? How do you find the unit vector, right, with magnitude? So A cross B. So 40 minus negative 3 is 43. 6 minus 30 is negative 24. And 6 minus negative 16, 6 plus 16 is 22. Oh, I'm not doing that in my head. Somebody could check that, but I think it's 2909. And we're done. Okay, so I got two vectors. Hopefully it's as easy as cross a u comma v. Oh, it looks like it might. Oh, yeah, it did. Worked. So it gave us a third vector. That's orthogonal to both. You can kind of see that. The way this works is, see how it's dotted there? That means it's like on the other side of this gray plane. Next unit is all about planes. A little tricky to see, but I think I can shift this over. Oh, I can do that. So orthogonal to both.